We talk a lot about the brains of modern automation.
Mm-hmm. The advanced algorithms, the cloud computing.
Exactly. The AI models predicting failure. But we rarely talk about the nervous system,
Right.
the actual physical pathways that have to take a sensation like heat or pressure and get it to the brain without it getting corrupted.
It's the classic garbage in, garbage out problem, isn't it? You can have the smartest AI in the world, but if the signal coming from that sensor is just noisy or distorted,
Then the AI is just making high-speed mistakes.
that's it.
Exactly. And that's why I'm so excited to dig into this infographic today. It's called Mastering Analog Signal Conditioning.
A great one.
It's basically a schematic for that nervous system.
Mm-hmm.
The whole central metaphor here is a signal conditioning bridge. And frankly, for anyone working in, industrial IoT or control systems, this bridge is the difference between a working factory and a catastrophe.
It really is. And I love how the graphic lays it out left to right, which is the actual direction of the signal flow.
Yeah.
On the far left, you have the raw reality. That's the sensor input. And on the far right, you have the control system interface. But all the magic, all the important stuff happens in the middle, on that bridge.
So let's set the stakes here, because we aren't just talking about a thermostat in your living room. Let's imagine something like a chemical reactor.
High stakes.
Very high stakes. You've got a thermocouple measuring a critical exothermic reaction, and the environment is just hostile vibration, electromagnetic interference from massive pumps, tons of heat.
Right. And you're dealing with a thermocouple signal that is incredibly weak. We are talking millivolts, maybe even microvolts sometimes.
And looking at the far left of this infographic, that raw sensor input section, the way they draw the signal is perfect. It's a jagged, erratic line, and it's labeled with 3 specific characteristics: raw, nonlinear, and weak.
Those are the 3 horsemen of the signal apocalypse.
I like that.
Raw implies it has no protection. Weak, like we said, low amplitude, it can get drowned out so easily. But nonlinear, that's the tricky one. That's the one that trips up a lot of junior engineers.
Because nature rarely moves in straight lines, right? We want this nice, simple y equals mx plus b linear equation, where 1 degree of heat equals exactly 1 millivolt of output. The materials just don't work like that.
Precisely. Thermistors, thermocouples, strain gauges, their resistance or their voltage curves, they respond differently at 100 degrees than they do at 500 degrees.
So if you just fed that raw curve into a controller that expects a straight line,
Your readings would be wildly inaccurate at the extremes.
so our chemical reactor might be running 50 degrees hotter than the control room thinks it is?
And boom, that is exactly why we need the bridge.
Okay, let's step onto the bridge structure itself. The infographic shifts here to a blue section labeled Core Principles of Transformation. And the header image is a graph. It's labeled the transfer function,
Yeah.
showing output equals F of input.
This is the mathematical heart of the entire process. The transfer function it's the rule book. It's not just passing the signal along, it's actively mapping that messy input to a desired clean output. This is where we mathematically correct for that nonlinearity we were just talking about.
And there are 4 distinct circles right underneath that graph outlining the specific jobs this bridge has to perform. The first one is linearization.
Mm-hmm.
And the description is correct, nonlinear sensor output.
Right. So sticking with our thermocouple example, the signal conditioner applies an inverse curve to the signal it's receiving. It knows the physics of the sensor, it knows how that metal behaves, and it basically forces the output to be linear.
It straightens the line.
It straightens the line so the computer doesn't have to do, heavy calculus just to read the temperature.
But there is a trade-off there, isn't there? When we linearize analog signals like that, are we maybe losing some resolution at the edges of the curve?
You can, yeah. If you stretch a compressed part of the curve, you're also amplifying the gaps between the data points. But with modern conditioning, the circuits are so precise that the trade-off is absolutely worth it for the reliability of the data you're feeding to the controller.
Okay, that makes sense. The second circle here is filtering. The text says, eliminate unwanted signal noise. Now, in our chemical plant scenario, this is huge.
Oh, it's everything.
You've got 480-volt motors spinning right next to that tiny millivolt sensor wire.
That's 60 hertz hum EMI, RFI. It's an electromagnetic storm in there. Without filtering, that jagged line we saw in the graphic effectively becomes a solid block of static. You wouldn't see the temperature change at all. You'd just see noise.
The infographic uses a little funnel icon here. It's about stripping away the frequencies that just don't belong, right?
Mm.
Like a low-pass filter that lets the slow temperature changes through, but blocks all that high-frequency electrical buzz.
Exactly. It's discriminatory in the best possible way. It says, look, temperatures don't change 60 times a second, so anything vibrating that fast is a lie. Delete it.
I love that. Okay, next up is signal level adjustment. This is about changing bias and gain for compatibility.
This seems straightforward, but it's critical.
It's amplification, basically.
It is, but it's all about resolution. If your analog to digital converter, your ADC on the other side, reads from 0 to 5 volts, but your sensor only outputs 0 to maybe 0.1 volts, you're only using a tiny fraction of the ADC's capability.
You're throwing away bits.
You're throwing away bits. You need to apply gain to stretch that signal so it fills the whole 0 to 5 volt window.
You're maximizing the dynamic range. Got it.
Yeah.
Now, the fourth circle, this is the one that separates the pros from the hobbyists, I think. Impedance matching.
Oh, yeah.
It says, maximize power transfer, minimize reflections.
Impedance, Z. This is where things get really interesting. In high-frequency communications like radio, you want matched impedance to prevent reflections, ghost signals bouncing back. But for sensor conditioning, we're usually dealing with voltage transfer, not RF power.
Which brings us to that sidebar on the graphic. Avoiding loading errors. It gives a very specific formula. Z-in must be much, much greater than Z-out.
This is the golden rule for voltage signals.
Let's unpack the physics of that. This is kind of like the observer effect, isn't it?
That's a great way to frame it. Think of your sensor as a small battery with a very weak internal voltage. If your signal conditioner has a low input impedance, it acts like a heavy load. It starts demanding a lot of current.
And because of Ohm's law, drawing that current causes a voltage drop across the sensor's own internal resistance.
Correct. The sensor sags. You're actively changing the voltage just by looking at it. So to avoid loading the sensor, the conditioner needs a massively high input impedance.
It has to be almost invisible.
It needs to look like an open circuit to the sensor sniffing the voltage potential without drawing any significant current.
So the graphic's warning about preventing original signal distortion is really about protecting the measurement source itself.
Exactly. If you violate that Z-in much greater than Z-out rule, you aren't measuring the process anymore. You're just measuring the interaction between your sensor and your bridge.
Okay, so we've covered the theory, the principles. Now let's look at the essential circuit building blocks in this yellow section of the graphic. This is the hardware that actually does all this.
This is where we get into the silicon and solder.
It breaks it down into passive and active circuits. Under passive, we see bridges and filters, and specifically the Wheatstone bridge.
A legendary circuit, absolutely foundational.
It looks like a diamond shape made of 4 resistors, and it's labeled with R sensor and delta V. Why is this specific arrangement so ubiquitous for things like strain gauges?
Because it turns resistance into voltage, and it does it differentially. A strain gauge changes resistance by a tiny, tiny amount when you bend it. If you just tried to measure that resistance directly with a multimeter, the resistance of your lead wires would mess up the whole reading.
The noise floor would be way too high.
Right. But the Wheatstone bridge relies on the balance between its two legs. When the bridge is balanced, the voltage is 0. As soon as that sensor's resistance changes, the balance tips, and you get a voltage potential right across the middle.
So it's super sensitive to change.
Incredibly sensitive to change while ignoring the absolute values. It's a null detector.
And that leads us to the star of the show, sitting right in the center of the infographic, the active circuit, the op-amp.
The operational amplifier, the workhorse of the analog world.
The graphic lists its capabilities right there: amplification, summing, and differential measurement. We talked about amplification, that's the gain. Summing is adding an offset or a bias. But differential measurement seems to be the superpower here, especially with all that noise we talked about.
It is. This is the hardware solution to the noise problem. An op-amp has 2 inputs, an inverting and a non-inverting input. And what it does is amplify the difference between them.
Okay, so if I have that 60 hertz hum from the factory motor, and it hits both wires of my sensor equally.
The op-amp sees, say, plus 1 volt of noise on wire A and plus 1 volt of noise on wire B. It subtracts B from A, the result.
0 noise, that's common mode rejection.
Exactly. The op-amp ignores the common mode noise and only amplifies the differential signal coming from the sensor. That's why the op-amp is the real engine room of this bridge. It provides the high input impedance to prevent loading. it does the math for the differential measurement, and it provides the power for the gain.
It's impressive how much utility is packed into that one little symbol. The graphic really centers it as the pivot point between the raw input and that final output.
It connects the physics of the sensor to the logic of the controller.
Speaking of the controller, let's move to the right side of the bridge. Standard analog signal ranges. We've conditioned the signal, we've cleaned it, linearized it. Now we have to actually send it to the control system interface.
The handshake. You need a standard language everyone can agree on.
The infographic highlights 3 standards. Let's start with the one that seems to run the entire industrial world. Electrical current, 4 to 20 mA.
The 4 to 20 milliamp current loop. An oldie but a goodie.
I have to ask the obvious question then. We live in a world of high-speed digital field buses and Ethernet. Why is a standard from the 1950s still the universal standard for reliable long-distance signal transmission?
Physics. Physics keeps it relevant. A voltage signal like 0 to 10 volts is fragile over a long distance. Wire has resistance. So if you push 10 volts through a mile of cable, you might only get 8 volts at the other end. You've lost data.
That's Ohm's law again, V equals IR.
Exactly. But current. Kirchhoff's current law states that the current entering a loop must equal the current leaving it. If I push 20 milliamps into a loop, 20 milliamps will arrive at the receiver, regardless of how long the wire is, as long as you have enough voltage to push it, of course.
So it's immune to voltage drop.
Totally immune.
That makes it incredibly robust. And the graphic notes 4 to 20, not 0 to 20. This is the live zero concept, right?
Correct. And that's a huge safety feature. In a 0 to 20 milliamp system, if you read 0, does that mean 0 pressure or...
The wire is cut?
Yeah.
You don't know.
You don't know. But with 4 to 20, 4 is 0 pressure. 0 is a broken system.
Ah, so you get built-in diagnostics for free.
For free. Plus, that base 4 milliamps provides enough power to actually run the sensor electronics, in many cases, what we call loop-powered devices. It reduces wiring costs significantly.
That's a great point. You don't need a separate power supply wire going out to the sensor. It just eats off the signal line.
Efficiency and reliability. That's why it hasn't died.
Okay, next standard on the list. Pneumatic pressure, 3 to 15 psi. This feels a little steampunk. Are we literally sending air pressure as a signal?
We are. And before you dismiss it as a museum piece, think about a refinery processing hydrogen or jet fuel.
A highly explosive environment.
Right. Do you want any electricity, even milliamps, running to a valve in that environment, one spark and it's all over?
So you use air?
Pneumatics are intrinsically safe by their very nature. There's no spark. So the signal conditioning bridge converts the electronic command in the safe control room into a pressure signal that goes out into the field. 3 psi means valve closed. 15 psi means valve open.
So in that case, the bridge is literally a transducer. It's converting electrons to air molecules.
It's physics translation.
And the final standard, electrical voltage, 0 to 5V, labeled as interfacing with digital converters, ADCs.
This is the local language. Inside the control cabinet or inside the device itself, we usually step down to voltage because that's what the microchips understand. ADCs generally don't read current, they read voltage potential.
Okay.
So usually you'll have a 4 to 20 milliamp signal come in from the field, run through a precision resistor, and that converts it to 0 to 5 volts right at the input of the controller.
So the journey is complete. And we see that final image on the far right, the control system interface. It's a clean monitor with flat, stable graphs.
The illusion of perfection.
It really is an illusion, isn't it? The operator sees 350 degrees and just assumes that's a hard fact.
Yeah.
They don't see the jagged mess, the nonlinearity, the common mode noise, or the impedance matching that happened milliseconds before.
And that's the definition of good engineering. The complexity should be invisible to the user. The operator needs to make decisions based on the process, not worry about the sensor physics.
But looking at this graphic, you realize just how fragile that illusion is. If the bridge fails, if that op-amp drifts, or the filter isn't tuned right, the operator is flying blind.
Or worse, flying on false instruments.
Yeah.
That's where the mastering part of the title comes in. Signal conditioning isn't a nice-to-have. It is the absolute foundation of the data hierarchy. You can't have big data without good small data.
It connects back to what we said right at the start. In an era of IoT and digital twins, we tend to think everything is digital. But the world is analog. Temperature, pressure, flow, vibration.
They're all continuous analog phenomena. And they always will be. We can shrink the bridge, we can put the op-amp and the ADC right onto the sensor chip itself, but we can't eliminate the bridge. The physics of signal extraction doesn't change just because the processor got faster.
So signal conditioning is effectively the translator between the laws of physics and the logic of binary code.
I'd go a step further. It's the gatekeeper. It decides what information is worthy of being processed and what is just noise that needs to be thrown away.
That's a powerful way to look at it.
It is.
So here's a thought for everyone listening. The next time you glance at a dashboard, whether it's a sophisticated SCADA screen in a factory or just the temperature gauge in your car, think about the op-amps.
Think about that invisible bridge.
Think about the thousands of tiny silicon chips working furiously to reject noise, match impedance, and linearize curves, just so you can see a simple, steady number.
It's a hive of activity behind a calm screen.
It really is. Thanks for walking us across the bridge today. It definitely gives me a new respect for the hardware layer.
Always a pleasure to geek out on the fundamentals.
See you on the next deep dive.